This is ECE 4430 project number 3.
And we are Sang-Hoon, Joshua, Malik, and Arya.
So pictured here are the two transimpedance amplifiers and their respective DC and transient responses. You can see that for the first transimpedance, that the output voltage response is a function of the logarithmic input times the coefficient of the negative thermal voltage, and this coincides with the simulated result. It's good because for a large input perturbation, the output node voltage isn't really changed much. The second circuit got the same result with an added offset in there, and as a coefficient, it's a positive kappa use of T instead of a negative use of T. For the transient responses of both, you get an unstable ramp function, and for the feedback amplifier, this makes sense because the feedback is positive. For the input voltage responding to a change in the input current, with an added feedback term in there, you still see the same negative thermal voltage term, but you also have a negative feedback coming from the feedback, which is a kappa squared use of T times alpha, which is the feedback ratio between the capacitors, and this contributes to the input voltage. And then you also have the gain of the output stage of the second transimpedance, which is a kappas of n over sigmas of p. And the reason why it came out to this simple common source is because you basically have a PMOS in parallel with a cascode NMOS, and because the output resistance of the PMOS is significantly less, the cascode can be ignored. Here shows the time constant of the first circuit, which came out to be a C-sensor of the transconductance from the source, which you can also see that thermal voltage term in there. And again, for the gain of the first circuit, you have the thermal voltage over an I bias term plus a S times capacitance, which is a pole. And you, as a logarithmic, coming from the logarithmic response of the DC, the term you see in there is a thermal voltage, which comes from that expression as well, and that contributes to the gain. Here you have the gain of the open loop of the feedback amplifier, and then you also have the closed loop of the feedback amplifier with this source follower stage feedback being included in there, and also the open loop gain is being multiplied in there because the open loop gain is in units of resistance, which is what is needed for the calculation to make sense dimensional analysis wise. For the time constant of the second circuit, we get the output resistance times the output capacitance, which is shown as the output from the PMOS stage being multiplied by the load capacitance with the addition of the parallel combination of C1 and C2. And the calculated result for the speed up of circuit 1B over 1A, the feedback over the non-feedback, is that the second one was roughly 50 times faster.
Okay, here we have the transimpedance amplifier layout. We implemented a floating gate with the capacitor blocks seen at the bottom right hand of the slide. We also implemented a 90 kilo ohm resistor in order to achieve proper biasing for our circuit. In the top right hand, you can see our Whiston links for the complete implementation, as well as just the circuit without the capacitors and resistors, as well as just the resistor itself.
All right, you see here the simulation of the transimpedance amplifier. So on this plot, we have the AC response over a large bandwidth. So you can see that the peak voltage in millivolts doesn't exceed 800 millivolts, as according to the specification. And then when you look at the power, it's right around 1 microwatt for the entire band. And the half power bandwidth is 20 kilohertz, so we meet our bandwidth requirement. And then when we run an AC and a DC analysis and do a current versus voltage sweep, we can see that we have a slope of roughly kappa times UT, which agrees with the analytical result as presented previously. And then we can see our AC input sweep, you know, the output doesn't exceed 800 millivolts, as you can see. And then on the right, I have notated the biasing that we used in this circuit. And now you can see the transient analysis we did. We get a ramp output function as also reported in the analytical section as well. So our simulation agrees with our analytical results. So on the left here is the schematic for the transimpedance amplifier that we talked about. And you can see we have a floating gate implementation. So now let's talk a little bit more about this floating gate. So now let's apply the floating gate to a common source schematic.
Here we have our floating gate common source implementation. Again, we use the same capacitor blocks on the right-hand side of the screen, which are approximately 10 femtofarad in capacitance. We provided multiple contacts in order to make sure there's a good current flow between all components in the circuit. On the left-hand side of the screen, we can see our widths and lengths for the total implementation and also without the capacitors.
So here we have depicted the floating gate common source implementation. So you can see from the graph that as you increase V tunnel, the charge increases on the gate. And so basically when the charge increases on the gate, the Vn needed to remain in the high gain region decreases. So basically this means that we can have programmability of this so that we can customize whatever charge we want to have on the gate, and so we can force the circuit to behave as we want it to behave. And the gain that we've calculated here is 93.3 volt per volt.
Here is our folded cascode layout. Here we again provided a lot of context to make sure there's good current flow, as well as optimized our layout for the MOSFETs, in particular by combining drain-in sources that are on common nets, as well as minimizing all metal layers as much as we could. The total width and length is on the right-hand side of the screen, as you can see, with and without the approximately 300 kilo ohm resistor.
So here is our specification table and schematic for the folded cascode amplifier. On the left we have the table of specifications and the actual values that we measured in cadence. On the top right we have the schematic for the folded cascode. It includes a bias circuitry, which is shown on the bottom right, where the bias circuitry includes a bootstrap current source and some cascoded transistors for voltage biasing. Now, some concerns that we will address in the next few slides are the area, what affects the area, the power, and the temperature effects will have. Here are the analytical equations, where the highlighted ones are most pertinent to our design. So here is the folded cascode amplifier's AC analysis, where we look at the gain, phase, and then the phase margin and the bandwidth. As you can see here on the right, we achieve a gain of about 90 dB, unity gain bandwidth of 7.8 megahertz, and a phase margin of about 73 degrees. The blue line represents the gain, and the red line represents the phase. Now, the gain is controlled by the amount of current going through the biasing transistor, M tau, on the schematic, which is directly proportional to the overall gain of the circuit. There is an issue with the temperature sensitivity that this may have, because since temperature is directly related to the gain, the bandwidth, and the transconductance, since they all have the UT term. So here's our slew rate here. We sweep the input using a square wave in the high gain region, and we get that a slew rate is about 0.3027 volts per microsecond using a linear slope fit. The reason why the slew rate is a bit low here is because there's not enough current draw from the top PFETs providing the bias current. One way to do it would be to increase the W over L ratios. Another way would be to actually decrease the load capacitance. So here we have a common mode rejection ratio of about 74 dB, and on the right we have an integrated input referred noise of about 0.673 nanovolts per square hertz. So here we have on the left our output swing, where we measure the output voltage while tying V minus to 1 volt and sweeping V plus from 0 to 1 VDD. So we get an output swing of about 2.85 E negative 8 volts to 1.43 volts. And on the right we have an input swing, where again we did the same configuration, except we measured the voltage across the biasing transistor, M tau. And we get an input swing of about 0.07 to 0.25 volts.